Our next speaker is Charles Lawrence from USA. Charles is the Chief Scientist for Astronomy and Physics at JPL and will present us an overview of Planck. Please, Charles, the stage is yours.
Well, thank you, Anastina, Hans Christian, and organizers for inviting me to talk at this conference. The list of participants, up over 180 now, illustrates the advantages of remote conferences. A lot of participants possible, and it also reminds me, looking at the list of participants, the drawbacks, all the people that I've worked with for years, friends, colleagues, and possible new acquaintances that I can't see in person. So my job here is looking in the opposite direction from Hans Christian, who was rooted firmly in the present and looking at the future. Here, I've got a retrospective on Planck analysis and results, 2013 to 2020. The dates will be clear in a minute. Planck was launched in 2009. It started in 1992. It's an interesting date to contemplate. Penzias and Wilson recognized, identified the CMB in 1964. Papers came out in 1965. But 1992 is exactly halfway between Penzias and Wilson's identification of the CMB and where we are now. So Planck covers half the history of the CMB. And when I think about the hardware, the development of the hardware, the analysis, which of course started later, but the development of the analysis, it really encapsulates the history of the field quite spectacularly well. Planck flew at L2, as all astrophysics missions should. It was the third generation space CMB mission, and its goal was to measure the temperature anisotropies of the cosmic microwave background to fundamental limits down to 5 arc minutes, and also to measure the polarization of the CMB better than ever before. It had 2 state-of-the-art cryogenic instruments, 9 bands, and as Hans Christian said, 7 polarized, 2 unpolarized. Although the residual polarization of the unpolarized detectors in those 2 bands allows the creation of polarized maps at the 2 highest frequencies. Hasn't been done yet in public, but some of the people on this conference have done it and not published it yet. There were 5 releases of papers and data in sets, and I've summarized them here. The early papers in 2011 were all astrophysics, no cosmology. The results were based on 10 months of data. There was no release of the time order data themselves. Maps were released, and it was strictly temperature. Calibration for 10 months was on the solar dipole. In 2013, with PR1, data from 15.5 months were released, time ordered data and maps. Once again, temperature only, and once again, calibration on the solar dipole. This time, the science was a combination of astronomy, astrophysics, and cosmology. 2015, with PR2, the full mission data were involved. 50.5 months of LFI, 29 months of HFI. That was the lifetime of the helium-3 on board for the 10th Kelvin cooler. Time ordered data and maps, of course. IQU for LFI, I for HFI, and QU, but polarization not usable at low multiples for HFI. The calibration changed to the orbital dipole. There were now multiple orbits, so it could be used. Science was cosmology, a little bit of astrophysics in there, but mostly cosmology. 2018 with PR3, all the data again, time ordered data, maps again, IQU. There's a change here between 2015 and 2018. In 2015, the HFI data in polarization weren't usable at low L. The focus for HFI between 2015 and 2018 was improving the low L polarization. And in 2018, the temperature data for HFI were not updated in any significant way, but the polarization was much improved. Orbital dipole calibration again, and all cosmology. The fourth and final Planck collaboration data release, PR4, came out this year, back in September. The analysis pipeline was NPipe. Rayo will talk about that a little bit later this morning, this afternoon, whatever part of the world you're in. And there were significant aspects of the analysis that were different than before. But the most, I would say, if I had to put it in one sentence, the most important thing was LFI and HFI data were processed jointly for the first time, and the possibilities of the high performance computing environment were seized. To start on this process of iterative, all-encompassing analysis that Hans Christian was just describing with BeyondPlanck. IQU, of course, orbital dipole. Science was limited. I'll talk about results there, but there's a lot left to be done on the science with the NPipe analyzed data. And there's considerable interest in the community in doing that. We're starting to see the effects of that. Here's a summary of the Planck collaboration papers. And by Planck collaboration papers, I mean papers whose author list starts with Planck collaboration. Early results, there were 26 papers, 584 pages. 2013 results up to 32 papers, 992 pages. 2015, 28 papers, 1,067 pages. 2018 results, 12 papers, 661 pages. You see that the average number of pages per paper was going up. Things were getting more and more, well, shall we say, detailed. Understanding was better. The level of detail required was better. The intermediate papers were released one by one, not in an entire set. There were 57 of them, the last one being the NPipe paper in September. Total number of pages, 1,311. There's one Planck bicep paper. You'll all remember that, quite an important paper. In first combination of Planck with the data from a ground-based experiment. So in total, 156 Planck collaboration papers, 4,632 pages. As of last night, when I checked, 48,779 citations, 8,962 citations for one of the papers alone, the most cited so far, the Parameters 2015 paper. It will be overtaken by the Parameters 2018 paper in time, I have no doubt. There are another more than 226 papers by Planck team members that are not Planck collaboration papers, but were based on Planck data and written by people in the Planck collaboration. They just weren't part of the main program of Planck, so that they were, we called them external papers. Okay. Summary of papers, lots of results. I want to take one example of the development of processing. So what Hans Christian described is where things, how to go from the, say, Planck 2018 and go forward. This is looking back 2016, say, to 2020. For the 2013 papers, the CMB power spectra produced by LFI and HFI agreed over the first peak extremely well, but they disagreed with WMAP by about 2%. The significance was not overwhelming, but it was at the concern level. That was a puzzle for a while. In the one of the last of the 2013 papers, number 31, consistency of the Planck data, this started to get sorted out. And so this is kind of very early example of the kinds of things that Hans Christian is talking about. So for LFI, the full 4-pi beam response used in the dipole calibration needed improvement. Remember, this was calibrated in 2013 on the solar dipole. That made about a 0.2% difference in the power spectrum. For HFI, near side lobe estimates, this is out to about 5 degrees, needed improvement. Beam window function corrections were in the neighborhood of 1%. Time constants were also a factor. There's a relationship between the beam sizes and the time constants of the detectors. In 2013, we had to calibrate on the WMAP solar dipole, not the orbital dipole. But WMAP was calibrated on the orbital dipole. They had all of their data, many years of data by then. But the WMAP solar dipole errors fed directly into the Planck errors, and in particular, foreground errors in the WMAP solar dipole fed directly into the Planck errors, but didn't affect WMAP. They calibrated on the orbital dipole. We inherited the errors and the foreground errors in their solar dipole. So in addition to that, we had to correct for foregrounds, including unresolved sources. So what I've put in red are the number of things that had to be included in corrections. And after all of that, then LFI and HFI agreed well with it, within the uncertainties. Planck minus WMAP was a 1.5 to 2 sigma difference, so not really very concerning. Things were getting better, but just compare this list then with the number of things that had to be taken into account over the next years, the number of things, the number of factors that went into what Hans Christian was just describing. In 2013, the calibration errors were estimated as about 0.6% in the 70 gigahertz maps and about 0.5% in the 100 and 143 gigahertz maps. Now notice I've switched here, power spectra up here to maps down here. You can handle that. Planck 2018 and NPipe are better than about 0.1%. And you'll hear more of that. You've already heard a good bit of that. You'll hear more of that in later talks. Rayo, I think, will talk about that. And the improvement was a result of many, many factors. But think about this time scale of a couple of years on this slide compared to the time scale of the calculation in BeyondPlanck, incorporating these things, getting the calibration, all these factors together. That's a great illustration of how far things have progressed in the last decade. All right, systematic errors, always the hard part. Planck ultimately was not limited by systematics except at the lowest few multiples. And in fact, Hans Christian has given examples of how that plays out. And I think he would argue that, well, it's not strictly limited to the lowest few multiples if you're talking about 44 gigahertz, so forth and so on. However, I'm looking at it from the standpoint of all of Planck. The hardest systematics to deal with were not LFI systematics. The hardest was a combination on HFI of ADC nonlinearities, which was unanticipated before launch, way out of spec electromagnetic contamination from the 4K cooler drive electronics, which was known before launch, but which there wasn't anything that could be done about it. And all in the context of limited downlink bandwidth. In order to get the data down to the ground, HFI had to sum 40 successive readout samples. It was each half of a square wave modulation, the way the kilometers were read out. But because the samples were summed on board and not sent individually to the ground, sample by sample correction for these problems was impossible. My estimate, not confirmed or discussed with anyone else in the team, of how much work it took to deal with this problem is something like 100 work years. I'm confident I'm not off by an order of magnitude in that estimate. It was a huge deal, and it was, it dominated the Planck analysis. The second hardest was another HFI combination, the second hardest to deal with set of systematics. And that had to do with beams, time constants, and long cosmic rays. Cosmic rays that hit part of the structure where the time constants were long. An editorial comment here. There are no shortcuts in finding and mitigating systematic problems. Any systematic effect, if you're going to do anything about it, has to be connected directly to its hardware cause. You have to be able to reproduce it with simulations that are built on real behavior of the hardware. Of course, understanding the real behavior of the hardware is one of the essential aspects of data analysis. You measure what you can before launch, but you take the real behavior on the sky in space. You have to be able to reproduce it with simulations. And because of this combination of things, sometimes valuable techniques such as blind analysis and machine learning just don't help. Blind analysis is a way of avoiding, a technique for avoiding experimenter bias. Well, the problem with blind analysis is if you go searching after simulation to reproduce hardware effects, if you're blind, it'll take you forever. You have to do impossible work. So you just can't do it blind. And machine learning is good at finding correlations, enormously valuable for sorting through heaps of data and finding things to look at. But machine learning does not connect up hardware issues with the effect in the data. So my editorializing for the morning. Hans Christian showed these final maps. In a real sense, these maps and the polarization ones on the next slide are the legacy of Planck, reflecting what's in the time order data with the mediating steps of the analysis. So the maps will continue to improve as the kind of work that BeyondPlanck is doing continues. But it's the universe as it was 370,000 years after the Big Bang. These maps are quite pretty. And as long as you accept beauty in the eye, beauty is in the eye of the beholder, and are willing to say that one of the key factors in beauty of an astrophysical image is its value for our understanding of the universe, these are the most beautiful images ever taken in astrophysics. Separation of foregrounds from the CMB, a big subject. You are all familiar with all of the bands, the curves, the wiggles, the shaded areas on these two plots, temperature on the left, polarization on the right. This is from the first paper in the Planck 2018 results series, and it showed where we were at the end. One other comment that I'll make here, the CO10 transition comes in here at the 115 gigahertz. And in a way, from a design standpoint of the mission, that was accidental. The cosmologist that designed the Planck high frequency instrument knew about. CO, of course, but thought it would be off the edge of the band and wouldn't matter much because it was a narrow line, so forth and so on. In fact, at the level of detail of the Planck data, it mattered quite a lot. You could say, well, design the band so that you don't have it at all. But then the next band up, 217, is there for a good reason in terms of Sunyaev-Zeldovich effect. You wouldn't want to change this frequency, and there's a CO line smack in the middle of this band. So off the edge of the 100 gigahertz, right in the middle of 217. And I'd say it was a good thing that we had both of them and the one in 353 to figure out any of them. Here are the maps you've seen, temperature, polarization, and in my view, the prettiest of all of the Planck maps, polarized dust emission at 353 gigahertz. Blow it up, print it out, hang it on your wall. It looks great. The CMB, this is from the 2018 paper 1, and the outline shows a region that was not used for cosmology. We're going to talk about results, cosmology only, and where Planck ended up. A simple 6-parameter, simple in quotation marks, 6-parameter lambda CDM model fits the Planck data extremely well. And the TT, the TE, the EE, and the CMB lensing spectra are all consistent with each other under the assumption of base lambda CDM cosmology. Here are the assumptions that underlying lambda CDM. Physics is the same throughout the universe. General relativity is an adequate description of gravity. On large scales, the universe is statistically the same everywhere. The universe was once hot and dense and has been expanding. There are 5 basic cosmological constituents: dark energy that behaves like the energy density of the vacuum, dark matter that is pressureless, stable, and non-electromagnetically interacting, regular baryonic matter that behaves just like it does on Earth, the photons we observe as the CMB, and neutrinos that are almost massless and stream like non-interacting relativistic particles. The curvature of space is very small. Variations in density were created early and are Gaussian, adiabatic, and nearly scale invariant as predicted by inflation. The universe has trivial topology. In particular, it's not periodic or multiply connected. So these are the assumptions underlying lambda CDM, the simple in quotation marks model. There's clearly a lot that goes in here. The ones that are colored in blue are tested directly by Planck. 4 and 5, well, the universe expanding, so forth and so on, is already demonstrated by the existence of the CMB and the direct measurement of the expansion of the universe, and the 5 basic cosmological constituents are already firmly established before Planck. But Planck can test all of these, did test all of these, and the results are that those assumptions underlying lambda CDM are confirmed at a level that we'll come to in a minute. The 6 parameters, just to write out, you're all familiar with these. They're color-coded in a way that I like to think of them as what period of time in the development of the universe they are related with. So initial fluctuations, 10 to the minus 35 or so seconds after the Big Bang. Baryon and cold dark matter density, first few minutes, and the precision of Planck's determination of these parameter values is really quite high. Sound horizon is first 370,000 years, and the reionization optical depth, age of the universe. Put all those together, the model fits the temperature data extremely well. Now, I've used the 2015 results. The figure that we have in the 2018 results paper works better on a portrait format page than the landscape format page. So I just used the Other ones at the level of a view graph, you can't tell the difference, although there are differences. And the fit then for TE and EE. The red line is the model that fits them all the best, and it's not an individual fit to one or the other. You have spectacular agreement between inferences from temperature and polarization. The lensing potential in this map shows all the mass in the universe, measured at about 40 sigma. This is from 2018. Here are the model parameter values. The N-pipe analysis that came out this year only updated one of these parameters, tau. But let's start from the top. So the physical density of baryons and cold dark matter in units of 18.79 yoctograms per cubic meter. The angular scale, the sound horizon, the slope and amplitude of the initial power spectrum. And the individual values are, of course, interesting and important to describing the universe. But for now, look at the number of sigma represented here. This is from Planck plus BAO in the 2018 results paper. All but tau are measured to better than 1%. When I was in graduate school, we knew one cosmological parameter in a different basis set, of course, but it was the Hubble constant. And it wasn't known to a factor of 2. And now we've got a complete description that's known to better than 1% for all but the reionization optical depth. Down here, some of the derived parameters that fall out of the model. Interesting. Spectacular progress. It's fair to ask, well, but lambda CDM, is it right? Is it wrong? I'd say that's not the way to look at it. Of course, it's not complete. In that sense, it has to be wrong. Certainly, it can't be exactly right. It's on a foundation of general relativity, which at least at high energy, small scales, is not a quantum theory. We think can't be right. So the question is, how wrong can it be? And these numbers say how wrong it can be. That's how well it fits the universe. So yes, not correct, but not very wrong. Spectacular progress. Think about that 56-year history of the CMB and how far we've come. We can check consistency with other data. I have a list here of things that would be possible to check. I'm only going to show results on the first two. They all could deserve or could stand long discussion. Here's baryon acoustic oscillations, and here's a plot of the acoustic scale distance as determined by the experiments plotted compared to that of Planck. So if the ratio is 1, you have agreement with Planck. And I've written out what the acoustic scale distance ratio is in detail. But the story here is that acoustic oscillations at the redshift of the CMB and at redshifts below 2.5 tell the same story about the distance scale. The one model fits early, fits late, and fits in between. So spectacular agreement. And as new BAO measurements have been made, this plot just gets more and more impressive. This is one of my favorite plots because it incorporates all of the forces of nature. Strong and weak, nuclear forces, electromagnetic and gravitational. The green stripes are 68% uncertainties in nuclear reaction rates and on the neutron lifetime. Horizontal bands show the observational bounds on primordial element abundances compiled by various authors. We've got helium up at the top, deuterium at the bottom. The red vertical band shows the Planck TT plus low polarization BAO bound on baryon density, the BBN predictions, and the CMB results shown here assume that the effective number of neutrino species is 3.046, no significant lepton asymmetry, and you see the agreement of these could hardly be better. So spectacular agreement between physics, cosmology, factors, all four forces of nature. This is a thing of beauty. This is another chart worth framing and hanging on your wall. Do more complicated models fit better? Well, the lambda CDM model fits really well. Can you improve it?